This video discusses the basic ideas behind hypothesis testing. This is also called null hypothesis significance testing. And you'll see this referred to as NHST in a lot of discussions. So, hypothesis testing is a yes or no proposition, a way of substantiating a theory or claim about some measurable quantity. The scientist, the researcher, comes up with the research hypothesis. It's a claim to substantiate. For instance, we think the mean is less than 14. So maybe 14 days to incubate coronavirus. Okay, this claim has to be backed up with strong evidence in order to be substantiated. The logical opposite of this is what's called the null hypothesis. And the null hypothesis just says, no, whatever your claim is, it's not true, it's the other way. Notice that the null hypothesis always includes an equality of some kind. Failure to reject the null hypothesis does not substantiate the null. Does not substantiate the null. A comparison or analogy would be a jury trial. Innocent until proven guilty. That's the null hypothesis. Requires strong evidence. To convict. So the concept's pretty straightforward. We've seen it in everyday life, but this is how we use it in science. So what constitutes strong evidence? Well, consider the claim that the mean is less than 14. Let's look at a set of different sample means and see if they indicate strong evidence. Well, the first one, 15. 15. That can't be strong evidence. That's not even less than 14. So that's ridiculous evidence. How about 13.9? Well, it's certainly less than 14, but only by a tiny little bit. Now, remember when we talked about estimation that there's some variation around the sampling mean, and so it's possible that it could be a little bit smaller, but it could also be a little bit larger. So this is weak evidence. And so that's not going to be convincing either. What about 6? 6 is a lot smaller than 14. This is a long distance. And so this is strong evidence. But that seems a little bit arbitrary. So how do we determine the difference between weak and strong? So how do we determine what's strong evidence? We're going to define an unlikely region under the null distribution. All right? And so, for instance, if we think the null is right here, all right, then we want an unlikely region, and we'll say this region is unlikely, all right, and we'll define it by something called a critical value. And we can calculate that using the null sampling distribution. And then if evidence falls in this region, we'll reject the null hypothesis. So here's the procedure. State the research and null hypotheses and the type 1 error alpha. Okay? And so this is numbers between 0 and 1 and close to 0. %5 is often used. Then, collect the data, calculate the test statistic. Compare the test statistic and the critical value. If the test statistic falls in the critical region, reject the null. Let's do some examples. We're going to assume that we know the variance, or standard deviation, and the sampling distribution then becomes Gaussian, and the test statistic is this z-score. Now notice, this is pretty much your standard z-score, but it's the score applied to the mean rather than to a single value, and that means that the denominator is the standard error. So here's an example of a one-sided test. One-sided, we want to go on the low side. So the research hypothesis says we're less than 14. The null hypothesis says 14 or larger. And I'm going to use this sample data. Sample of size 36. We got a sample mean of 13.1, and our standard deviation is known to be 3. So we'll go ahead and calculate the test statistic. Well, first we'll do the critical value. We're on the low side, so here's our alpha, 5%. We'll look that up in the normal table, and we'll get a critical value of 16.45. Then we'll go ahead and calculate the test statistic. So sample mean minus null mean divided by standard deviation by the square root of the sample size. A little bit of calculator work says this is minus 1.8. Okay? So minus 1.8 is out here. And so we're going to reject the null hypothesis. Nice. Let's do the other side. Another researcher comes along and says, I think the mean is greater than 14. Then his null hypothesis is 14 or less. He collects his data, sample size of 64. He gets 14.3 for a sample mean. That's encouraging. Same standard deviation, 3. Now the critical value is on the high side, so now we go up to 95% because the 5% is up here. So now the critical value is plus 1.645. Take the sample mean minus the null mean, divide by standard deviation, scaled by the square root of the sample size, and we get 0.8, which does not exceed the critical value, so do not reject the null hypothesis. How about a two-sided test? So now we're not sure whether the value is 14 or not. We think perhaps it's not 14. Then the null says, well, it is 14. So we have to see if it differs. This time, since alpha is 5%, and we can go either way, we have to look at alpha by 2 is 2.5% on the high side and on the low side. So now we have two critical values, but by symmetry it's just plus or minus. So look up 2.5% on both tails, and our critical values are plus or minus 1.96. Plug in our values, sample mean minus null mean, divided by standard deviation scaled by the square root of sample size. We get 2.0. Woo! Great. Reject the null hypothesis. Now, many researchers do something called pre-registration. They actually publish the first two parts of their hypothesis testing. So test, part 1, claim, part 2, critical value sampling distribution. And the reason to do that is to keep themselves honest, okay? Because it's possible to peek at the data and tweak the test so that you get the desired outcome. Let's look at two similar tests that use the same sample statistics, both with the same alpha, 5%, and the same null mean, 10. So we have a sample size of 25, a sample mean 10.7, a standard deviation of 2. We calculate the z statistic, and we get 1.75. Now, if we're cheating, we're going to compare these two tests. The first one is a two-sided test, so the research claim is the mean is different from 10 versus the mean is 10. This has a critical value of 1.96. We do not reject the null because 1.75 doesn't fall into the critical region. However, if we do a one-sided test where we claim that the mean is greater than 10 versus no, it's not greater than 10, then the critical value is 1.645 and our test statistic falls in the critical region and we reject H0. This is why we do pre-registration. No peeking. Finally, the situation that we all really find ourselves in. What if I don't have an alpha value? Nobody gave me an alpha. What do I do? Well, it turns out that when Fisher invented Null Hypothesis Significance Testing, his method was to directly evaluate the evidence and generate what's called a p-value. A p-value. Okay? P-value measures is the strength of evidence. Small p-values indicate strong evidence. Okay? Obviously, p-values are not from Texas. Because in Texas, everything that's big is better, and p-values smaller is better. So we're going to reject when we have a very, very small p-value. Now, what if you do have an alpha? Well, take your critical value, compare it to the p-value. Okay, so here's the p-value. P-value is defined by the test statistic, or z-score. So it's this little tail here that's defined by the data, and if that tail is smaller in probability than alpha, then you reject the null. So p-value less than alpha, reject the null. That's all there is to p-value, but be careful with it.